So good evening everyone. So today we are going to look at the continuation of the topic bioorganic chemistry. And in the previous video we were talking about carbohydrates, the definition of carbohydrates, and what is the prominence of carbohydrates in the field of organic chemistry. So today what we will look at is how to draw the cyclic structure of D-glucose and D-fructose. Or maybe we will look at D-glucose first and then we go into D-fructose. Okay, so we do know the structure of D-glucose is here. So you can see that the structure of D-glucose is here. So this structure we call as the Fischer projection. So already, in the previous videos of mine, I've already expressed how you're supposed to write a Fischer projection and what the horizontal bonds mean and what the vertical bonds mean. And as per the nomenclature of organic molecules, that is the stereochemical nomenclature, the molecules that are written, the most oxidized carbon is supposed to be at the top of the molecule, and that's why you will see that in the case of aldoses, the aldehyde group will be at the top of the molecule, and that is the least oxidized group. The CH2OH group will be at the bottom of the molecule. Okay, now how do you go about writing the structure of these molecules? So you can see that here. So now this molecule has to be written in a horizontal fashion. So what you do is you write this molecule like this. So you put the 4 lines here, and you mention the CHO group here and the CH2OH group here. Leave the mention however. So this hydroxyl group is supposed to be here, and the next hydroxyl group is supposed to be on the top. And you'll have 2 more hydroxyl groups here, here, and here, and then the CH2OH group here at the tail. Okay. Now what we do is we rotate this carbon alone. So this carbon is right here. So this carbon that you are seeing, maybe I'll use some other color to show you. So this particular carbon along with the CH2OH group and the OH group are here. Okay, so the remainder, that is, you can see this hydroxyl group, the first hydroxyl group here, it is here. The second hydroxyl group is on the top. So the second hydroxyl group is on the top. The third hydroxyl group is below. So I told you that we are going to rotate this carbon to bring the CH2OH group up. So this moves here. So you can see that the OH group on the 5th carbon is right here, and you have the CH2OH group. Now, now let's take a look. Now, the hydroxyl group here is going to react with the aldehyde. So what it can form? It can form an ester linkage. Sorry, it can form an ether linkage. So it can form a ether-like linkage. So it forms an ether-like linkage with a hydroxyl group. So this is going to turn into a cyclic ether. And here you have a cyclic ether on the same side. Okay. Now we know that aldehyde molecules are planar molecules because they have the pi bonds on 2 sides. So they're going to be planar molecules. So when the nucleophile attacks, they can either attack from the top or they can be either attacked from the bottom. So that's what happens here in the case of glucose. When the carbon of the carbon holding the 5th hydroxyl group, that is the 5th carbon holding the hydroxyl group, attacks the first carbon, C double bond O carbon. So what happens here is there are 2 products that can be formed. Okay, so the first attack is from the top, so the hydroxyl group falls below here. So it attacks from here, the proton jumps up here. So There is an OH group here that is formed. So this H jumps out here. So it forms an OH group. In a similar fashion, when it attacks from the bottom, you see that the C double bond O comes up and the proton jumps here. So you can see that it has jumped here. So now we have, two structures. So we have, two structures. The first structure where the hydroxyl group is at the bottom. That is, it points downwards from the surface of the ring. It is called as an alpha D glucose. Now, since it is a six-membered ring, we do remember, the pyran group, isn't it? So we remember the pyran group. So we remember the pyran ring, I suppose. So six-membered pyran ring. So that's why this is called as alpha D glucopyranose. And what will be the case of the second molecule? It will be a beta D glucopyranose. So those are the names that are given to these molecules. Now, see, after the reaction, there is ether that is formed, two ether cyclic ethers that are formed, and the hydroxyl groups are pointing in opposite directions. Now, the stereochemistry of both these molecules only differ at carbon 1. So, if you look at the stereochemistry of this entire molecule, both these molecules, the stereochemistry only varies about carbon 1. So, cyclic cyclic structures, that is cyclic sugars that vary with the stereochemistry around only their first carbon are called as anomers, or they are the isomers, which we call as anomers. So, you can see a better, view of both the, molecules going in, and you can see the rotation here. So you can see the rotation here, which I mentioned. Here you can see the rotation here, which I mentioned in the previous slide. So this is more sort of a more, loosened way of, representing the cyclization that has happened. Okay, and this is the chair form of the sugar that is going to be formed. So you can see here that here you can see that the hydroxyl group is in the equatorial position, and here the hydroxyl group is in the axial position. Okay, so this is your alpha D glucopyranose, and this is your beta D glucopyranose. Okay, so please draw these structures and practice repeatedly. Otherwise, you will have a difficulty writing these cyclic structures because of the multiple hydroxyl groups. If you miss out on the hydroxyl group, the entire structure goes wrong and you'll be losing marks. And these cyclic structures that are, these flat cyclic structures, instead of the chair structures that have been mentioned here, these structures are called as Haworth projections. Okay, so I stop here. We'll come back to the case of fructose. Okay, thank you so much, dear friends. So please work things out.